Okay. Can everybody see this all right? Okay, good. Sorry, I'm very paranoid about this. I use Linux and nothing ever works. Okay, so this is the collab environment. This is what it looks like. This is what executing code and it looks like. The idea is that it's an interactive programming environment that allows you to break up your program into sections called cells. It's really nice for a lot of reasons. If you're used to just programming in scripts, you're used to the idea of getting your program and writing it in a single text file, and then your interpreter or your compiler or whatever the case might be deals with the entire file at a time, and it executes top to bottom. This programming environment is kind of cool because it breaks your program up into smaller pieces and you can execute them separately, but it's all still fundamentally happening in the same execution environment. So it's a really nice way to iterate and experiment and practice different things. And this is kind of a lame example here. We're actually going to see it in more detail when we get into the coding section, and I'll kind of talk through how it works when we get there. But I should point out that if you want to follow along and if you want to code along with this, go into your Google Drive, um, go to New, and all the way down here, there's more. If you have not yet set up Colab or ever used Colab before, Colab is the environment that Google provides that allows us to use this programming environment. You're going to want to go down here to connect more apps at this point. Click here, and then you will find Colab in here. You can search for apps available in Google Drive. It's called Collaboratory. That's the whole thing. So yeah, so you would click on this, and then there'll be an install button, and all that's going to do is just give the Colab environment access to your Google Drive, or maybe the other way around. I'm not completely sure, but the whole point is that once you click the install button, then you'll be able to go to this new menu here in Drive, and then under more, you'll see, sorry, Google Collaboratory available right here. That's all. So once you do that, you will have access to this. You can click on this and you can make a new collab document like this, and it will just be sitting in your Google Drive. It'll be a regular file, just like if it was a text document or spreadsheet or whatever. So get that done, just so that you can make one of these files in Drive. If you have any problems or questions, you can either ask me about it or ask Chris too, and he can help you out. So as long as you can get to this and you can see what I'm seeing on the screen right here, then you're good and ready to go. So just
Yeah,
throwing
and
that out there.
if y'all want to, while he's talking, if y'all want to, you know, throw me your tech support questions in chat, then I'll see if I
Yes,
can help everybody get set up who's not.
Chris will be much more better equipped to help than I will while I'm talking about the language modeling stuff. So yeah, talk to Chris about it if you're having trouble. But basically, yeah, print hello world. And you can execute with Control Enter, or you can hit the play button off to the side. Either does the same. Maybe just see if you can get to this point where you can do hello world in Python and Colab. And if you can, then you're good. But anyway, I will close all this and let me get rid of these because I don't want these. And so with that out of the way, we'll get into the actual material now. So intro to language modeling. So hi everybody. My name is Matthew McNeill. I also go by Matt. Either is fine. There's my email address. You'll get these slides afterwards too, so don't feel like you have to take notes unless you really want to. So my deal is I'm a former professional software engineer. I was one for about 9 years before I decided I wanted to get a PhD, so I went back to school. I'm getting my PhD at the City University of New York Graduate Center. It's fun place. It's a lot of cool stuff going on there. My research area is sort of hard to pin down, but it's natural language processing, if you want to get into the big category that describes it best. Some things that I have worked on are speech synthesis. My main field of study is what's called conversational dynamics. So it's just the study of how people talk with one another and their behaviors. I do a little work with spoken dialogue systems as well, kind of relates to conversational dynamics. We're studying speaking with computers instead of speaking with people. And I guess the thread that ties all of those things together is that they all make extensive use of machine learning. Some people study this stuff and never touch machine learning, but I've been using it pretty consistently throughout my time here. And so with that as a kicking off point, I'd like to just very briefly talk about machine learning and artificial intelligence very briefly. I had a whole larger talk about this, but since we're focusing on language modeling, I'll just give a quick introduction to this. I did want to show this picture because I love it and I think it's hilarious. On the right is actually what is arguably the world's first neural network. I'm sure most of you have heard of neural networks before. Maybe some of you used them before. The very first one was physically built and it was real. And that like rat's nest of wires was what was required to hook it up and make it work. It was made in the late 1950s. And it actually did something that is recognizable as a machine learning task today. It would perform what we call binary classification on a 400 pixel image. So the question it might be answering is maybe, let's say the image was of the letter A. The problem would just be like, is this the letter A? Yes or no? So you could feed it pictures of the letter A and it would say yes. You could feed it pictures of things that aren't the letter A and it would say no. And that was what it did. The reason I love to bring this up is because, I think we're in the middle of a big hype cycle around language models right now. And it's funny how history tends to repeat itself. There's a quote from the New York Times that this is the embryo of an electronic computer that the Navy, it was the Navy doing this, expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Um, at the time, this was what people thought this model would be able to do. Looking back on it, you could probably do this on a pocket calculator in sort of using modern technology. So that entire cabinet there, as is often the case with computers, got reduced down to a trivial operation that you could just do on any computer that's available today, which I think is hilarious. It did not end up doing any of those things, but I suppose maybe we're closer to those things now than we've ever been before. Machine learning, here's a couple definitions of the field of machine learning in general. It's a really complicated, deep topic, and we're only going to scratch the surface of it today. But I like this quote up here at the top. Machine learning is the field of study that gives the computers the ability to learn without being explicitly programmed. That's actually a concept that we're going to examine a little bit today. Essentially, what we're going to do is write a program that learns how to output text that looks realistic, that reads like plausible, realistic text. It's not going to be anywhere near ChatGPT, but that's fundamentally what's going on. None of us are going to tell it how to do this. It's just going to learn by doing a very clever analysis of a big piece of text. There's a more formal definition at the bottom, but I won't get into that because I don't want to bore everybody too much. I will add this because I think this is useful framing. There's a relationship between machine learning and artificial intelligence. Machine learning is often considered a subfield of artificial intelligence, but artificial intelligence as a field is much broader. And in fact, machine learning is really just the study of, like, ultimately, if you ever get down to it and you decide to start studying it and work with it, ultimately, at the end of the day, all it really is really advanced curve fitting. Mathematically, that's what's going on, and it is a tool that can be used in a broader toolbox of artificial intelligence as a whole. Machine learning is a very specific field with very specific problems and very specific approaches to them. Artificial intelligence more broadly is a field that seeks to build intelligent systems, and it will use any technique that's available to it that seems to work, one of which is machine learning. And I think this is a really good map of the field of artificial intelligence as a whole. There's two dimensions here. So if we look at the chart along the y-axis, looking at the columns, or sorry, looking at the rows, we're concerned with thinking and acting. So there's this sense that with artificial intelligence, we're actually wanting to emulate the thought processes that go into doing something smart. Or acting, we're just interested in the outer effects of that, let's say like with behaviors and things without thinking about what's going on the inside. And then the columns here, humanly and rationally, we're interested in thinking like a person does or acting like a person does. or we're interested in rationality. So just making the best decisions given a set of circumstances. And so with this chart, we can see that there's four kind of broad research areas or focus areas in the field of artificial intelligence. We can study how to think humanly, which is we're literally thinking about how to emulate the way that people think about problems. We might be interested in thinking rationally. That is, we're only interested in reasoning logically, and that has nothing to do with maybe the more complicated thought processes that people go through. We might be interested in acting humanly. So we're not interested, again, like I said, in the processes that's going on, but just the outwardly visible behaviors. We want something that looks human or looks like something a human would do, but we don't care how we achieve that goal. Or we might be acting rationally. That is, we want to behave in a way that achieves an optimal outcome or the best possible outcome. And there's actually a lot of really cool research that falls into all four of these categories. For instance, I used to know a professor at another university that was doing research in modeling how vision works. So he was actually using machine learning techniques to emulate the mechanics of the eye and the methods of perception that the brain uses. And I would say that falls into the thinking humanly approach because it's literally trying to model how a human brain works. Um, Thinking rationally, this is a bit older. They don't tend to do as much research in this now as they used to, but there's a whole class of programming systems that are designed to reason through logical propositions. And there's software that you can do where you can feed all kinds of logical statements into it, and it'll start making guesses about sort of natural consequences of all of those logical statements. It's really cool stuff. Where the majority of artificial intelligence research tends to be now, or at least the higher profile sides of it, tends to be in these two categories, which is acting either humanly or rationally. And I'm actually wondering if anyone maybe has some guesses about some types of AI systems that they might have seen or interacted with that falls into one of these two categories. Just throwing that out to the room.
As usual, we can use the raise hand feature.
Yeah,
Um,
or you can just jump in. Yeah. See you, Michael.
Billy?
Yeah, well, the the humanly thing is like it's interesting that you brought this up because I know that one of the things that somebody asked me at one point as like a metric for like, well, how good has AI gotten rationally is ask it like I don't know how many R's are in race car or something like that. Like ask it questions like that. Like ask Claude or ask ChatGPT and it'll get it wrong. It'll say like 2 instead of 3 or whatever. Or
Yeah,
so
and so that's actually an example of not thinking rationally, right? Because like there's not like any like the race car example, right? There's not really any real subjectivity or opinion in that. There's that word just has a certain number of R's in it. And I would say counting that as a very just like automatic process that any like that we would engage in. I don't know, maybe I wouldn't pin it there exactly, but I would say maybe just to put this out there that ChatGPT and other similar systems are designed to act humanly. That is, they're designed to behave in a way that appears, or they're designed to behave in a way that appears to be what a human would do, in a very specific context that we're going to look at later in this lecture. And then when you ask it to do something rationally, it sort of doesn't work as well because it's not designed to do that. Like that's just not how it works. I saw another hand, Michael.
You already said it.
You did? Okay, ChatGPT.
Yeah.
ChatGPT is acting humanly. Here's another one. I think a lot of people don't necessarily think of this as artificial intelligence, but it often tends to get lumped into it. Pathfinding. The idea that you can find an optimal pathway um, between two different points. I think maybe if we were to go back up here, that might be like like if you were thinking about a like a self-driving car, right? And you wanted to get in it and you would not think it was particularly intelligent if it took the long way to get to your destination or if it drove off a cliff or something like that. We would not think that that's a particularly rational behavior for a car to engage in. But if a car picks a good path that gets you to your destination very quickly, we might say that that car is behaving rationally. Like I said, machine learning is a small part of artificial intelligence. It will take whatever it wants. It doesn't care. And if a simple pathfinding algorithm is something that can create the impression of rational behavior, then it'll take it and use it. And we tend to interpret machines that way. Michael, I see your hand up again.
I don't see it. I'm sorry.
Oh, okay. Yeah, sorry about that. Okay. Yeah, so here's a whole bunch of things that I think fall into these categories. So yeah, there's self-driving cars. There's a few other examples too. I like this one. Machine translation is a great example of taking something in one language and trying to put it out as another. I guess depending on how you want to look at it, that's probably acting humanly or acting rationally, depending on your goals for the translation. Maybe you could have like a more of a artistic sort of side to the translation where you're doing something like, oh, this is something that a human would find aesthetically pleasing or nice, or rational, meaning you want the most literal translation possible. Other stuff in here, document summarization, robotic vacuums, chess engines. Maybe just be thinking about some of these and where you might put them on this map for different kinds of artificial intelligence. But like I said, with language models in particular, more often than not, they tend to fall very squarely in the acting humanly category because we're trying to emulate the writing behavior of people, which is a very, very human thing to do. One last thing that I'd like to talk about. So I did mention on a previous slide that a good definition of machine learning was a program that can learn from data without being explicitly told what to do. And to maybe be a little bit more specific about what that looks like, here's a extremely rough approximation of the software development lifecycle. Maybe this is something that might seem reasonable to you, having been studying programming for a while. I guess this depends on what methods you're using or how you tend to approach it, but you tend to approach problems in a way where you study a problem, and I'm using this abstraction of writing rules. Essentially, that's what writing a program is. You're just stating a bunch of things that you want to happen or conditions that need to be met or things like that. And by writing and accumulating a set of rules, you can come up with a program that accomplishes a particular task. When you're done, you evaluate it, and either it works and you launch it, whatever that means for your program, or you find that it has made mistakes. And if it makes a mistake, then that means that you did not adequately understand the problem or express the solution to it. That's a bug, right? Bug comes from the program doing something that you didn't expect because you made a mistake. So you go back to study the problem again, you write more rules, you do more programming, and then you evaluate it again until it either does what you want, you find more problems, and you just go back and fix it again. With the machine learning, it's very slightly different, and also kind of very similar. In fact, there's only one thing that got replaced here, but the thing that got replaced is enormously significant, and it's something that we'll see in the second part of this slide. You study a problem, and then instead of writing rules, you train a machine learning model. The idea being that instead of having to manually enumerate the behavior of your program, like you would do if you were just writing a typical sort of program, instead the machine learning model is learning an approximation of those rules by observing patterns in data. That's it. You evaluate it at the end, and in other words, you look at it and you decide whether the machine learning model that you just trained is good at solving your problem. And if it's good enough to the point that you're happy with its performance, you can launch it. Otherwise, you go back, study the problem again, and try something different. But the main difference here is that with a typical software development lifecycle, you are the one who is deciding how the program works and what decisions are made. With the machine learning model, you are not doing any of that. You're allowing the model to make those decisions on its own based on what it observes in the data. So with that out of the way, let's get into language models and text generation. So I don't know that I necessarily need to introduce any of these. They're pretty well known at this point.
I'll throw it out to the group here. Does anybody not know any of these?
I threw Eliza in as
Eliza.
Yeah, what is Eliza? Anybody heard of Eliza? No? Okay. This is my favorite thing, and this is such a case study in just that acting humanly category that I was talking about earlier. It was one of the first chatbots, and it presented itself as a therapist. And this was in 1966. This was before we had any like, big machine learning approaches or even the computational resources to do what I'm about to propose that we do. All it would do was take what you wrote and rephrase it as a question. So if you came to it and said like, oh, I had a bad day today, it would ask like, why is it that you had a bad day today? And the people who wrote it were just like messing around, and they looked at the logs of it, and people were just pouring their heart out to this thing, like that it actually like came off to them as a real therapist, and they talked to it. And again, all it does is take your statements and rephrases them as a question. It's easy to break, but it engaged people still, and people were willing to engage with it as though it were a therapist, and they talked to it, and I just find that fascinating. So
had-
you know,
I think we had a question or
oh, did
two.
we?
Yeah,
I don't
Jennifer. I saw
oh,
Jennifer's hand
okay.
go up briefly.
Yeah, go ahead. Sorry, I thought that the hands bubbled up to the top, but they don't. Yeah, Jennifer, what's
I didn't have a question. I was just going to talk about Eliza.
oh, you knew about Eliza. Okay.
Has anybody used Eliza?
Highly recommend it. It's a fun fun little
I know I
exercise.
have, but I can't remember like where or how. Like I guess it just I just remember it saying a lot of how does that make you feel?
Yes.
Well, I was gonna say, I don't know if the things go to the top, but I had my so
Oh yeah,
go
I
ahead.
noticed that too. Yeah, sorry, go ahead.
yeah, so like I don't know if anybody in here knows what Smarter Child is, but if you do, then
Oh,
that's
that's another one.
that's actually not, well, I'm pretty sure it's not machine learning, because what they did with that, then this was like a AOL Instant Messenger chatbot from like the early 2000s that I used when I was a kid, like because it was really funny. It was like the way that they made it was it's basically like it like just hard programming. Like you give a response that's kind of you give an input that's kind of like this, and then it says, okay, if it's this, then say this. So somebody actually hard programmed that in. So that's that is AI technically, because it's supposed to artificially look intelligent, but it's not machine learning because it's hard programmed rules for, you know, if this happens, then do this. If this happens, then do this. So it wasn't really trained, you know?
Yes. Yeah, I've heard it. There are variations like that, and the same is true of Eliza. It was not machine learning; it was entirely rule based, and that's part of the reason why it's as easy to break as it is. I do highly recommend you go talk to Eliza. There's also a variant Azile that is just mean to you, but but it works the same way. Yeah. But yeah, so let's talk about how these things work. And so maybe I should preface what we're about to talk about, that what we're about to discuss today is fundamentally how modern language models work. This is how ChatGPT works. This is how Claude and Copilot work. This is just an extremely simple formulation of the same problem. So while we're not going to be doing any highly advanced machine learning, like the type that we'll talk about a bit later in the talk, what it is that there is a question that is asked repeatedly. And the way we ask that question and the way we answer that question is fundamentally at the heart of how ChatGPT works as well. And so even though it's not directly translatable, a lot of the sort of just approach to this problem can translate directly over to how ChatGPT works as well. So my hope is that by the end of this, you'll see that what we're about to write is an extremely simple language model that is barely capable of even like a tenth of the things that ChatGPT can do. But understanding how this language model works might help you understand how ChatGPT works a little bit better. That's the goal. By the way, I just lost my participants view and I'm not quite sure how to get it back. So if you have a question, maybe just I'll insert pauses and ask for questions occasionally. And if you have one, you don't need to raise your hand. You can just ask. Okay. So let's start generating text just on our own. There's a term I need to bring up, which is called the prefix. And let's just say that the mechanism we use to choose the prefix is random. We'll just pick a random word. I randomly selected the word the. So the is the prefix. And so the question is, given a prefix, what word comes next? So I suppose I'll throw this out to the room, and you can just jump in if you want to answer. What word comes after the?
Car.
Chatbot.
The car. Okay, why car? Why did you pick that?
It's a noun. It's a person, place, or thing.
Okay, interesting. So you use some criteria to decide which word came next. So out of all the possible nouns, then why did you pick car?
I think because it was short. It's really early in the alphabet.
Yeah.
It's a common object.
Okay. Well, so that
Um,
I think you brought some context to the party, right? You kind of had some criteria that made the word car seem appealing to you. And so out of all of the possible words you could have picked, you chose car for the reasons that you just stated. I mean, sure, why not? What's an alternative? I heard somebody else say chatbot. Why chatbot? No, okay.
Well, I have one, but it wasn't
Hmm.
made by me. I've been taking notes with Claude as I've been doing this, and Claude said the quick because it said
The quick brown fox jumps over the lazy dog. Yeah, okay, that's a pretty common phrase if you're not familiar with it. That shows up in a lot of like fonts. I think font selection dialogues just because it uses every word in the English language. So you'll see it in like graphic design circles
Every
sometimes. So yeah,
word.
every letter in the
I
those are
said
all the words.
chatbot because I felt like that it had a high likelihood of being the next word in
Yes.
the context of this call.
Yes. Well, so actually, I would say that it's impossible to answer this question in any reasonable kind of way. And we already kind of touched on a few reasons as to why. There were a few words that came up when I was discussing this, but ultimately, what's the problem? The problem is that we're dealing with a natural language. How many words are there in the English language? Does anyone know, like a rough estimate? I don't even know. I mean, maybe somebody just knows off the top of their head, but it's a lot, isn't it?
50,000 would be my guess.
I'm sure. Let's go with that. That's a lot of words.
I think it's like 50, I think it's like 15,000 as your baseline, and then yeah, like maybe 50,000 as like the more complex stuff. But the more complex stuff often just builds off of previous words and roots that we already knew. So
Yeah, but it's not even just about words. It's also word usage too. I heard somebody, so when somebody said when you chose car, you picked it because it was a noun. That's actually a pretty reasonable thing for us to do as people to narrow it down because nouns very often come after the word the, like so like the car, the television, the building, the laptop, whatever. But that's not always true, is it? Because you could have like the blue car or the gray building or something like that. And then you're getting into noun phrases. But the word that follows the immediately is not necessarily a noun. So in fact, constraining yourselves to nouns could maybe make things a little bit easier. Isn't always accurate. We don't always follow the word the with the noun, but even if that's what we were doing, right? Even if we were saying we're only going to consider nouns and nothing else, that doesn't really make the problem any easier because there are so many nouns out there and we just lack any kind of reasonable context for this, right? Like we don't know what kind of sentence we're trying to generate. We don't have any particular goals here. Maybe some of you individually might have one, but for the purposes of this process, all I'm asking is you have the word the, what comes next? And there is no additional like motivation or goals in the process here. And if that's the case, I would say that that makes the question impossible to answer. Here's a few excuses. Some of these we covered already. So one is that there's so many English words that come after the. How can we possibly choose one? The by itself does not contain enough information to determine the rest of a sentence. So that's a context thing. And then Python, in this case, we are going to write in Python, but fill in with your favorite programming language. Doesn't know any words. So we can't really go and ask it for help either.
And there's a band called the. So it could even be followed by itself.
Yep, you could do that. would argue in that case that the is a noun, but that doesn't really help, actually. So
I think
yeah.
they were trying to break that, but yes.
Yes. Anyway. So here's how we're going to resolve the problem. The problem is that we've been asking this question, what comes after the word the, with respect to the entire English language. And in that comes the entire set of possibilities regarding, first off, all possible words that could come next, but then all possible sentences that we could make out of this whole thing. And it's just, I would say, impossible to enumerate them all. But if we were to constrain ourselves to a specific expression of the English language, that makes the problem a little bit easier to solve. And so we're going to use this to solve this by incorporating what we call in machine learning a corpus, or a collection of documents. And what we're going to do is make the assumption, and we will see in a moment how this assumption is faulty and kind of problematic, but what else can we do? A single document will will act as a stand-in for the English language as a whole. That is to say, out of all possible things that it is possible to say, given our knowledge of the language, here's one of them. Here's a book. Here's a document. Here's an article that somebody wrote. And is it suitable as a stand-in for the English language? Well, sure, because the person who wrote it used words in the language. They used grammatical constructs available to us in the language. And it's an example of how the language is used in practice. So sure, we'll use it as a stand-in for the language in the same way that in, say, a drug trial, a small collection of people acts as a stand-in for the population as a whole, right? When we do drug trials, we don't recruit everybody in the world to test out the drug. We recruit a small number of people and assume that they're representative of the population as a whole. And that's fundamentally the same thing that we're doing here. So here's what we're going to do to answer this question. What comes after the prefix the? Well, we will analyze that document and find all words that follow the word the. And then we'll just pick one at random. And so in doing so, we will allow that document to stand in for the English language in a way that helps us answer this question. So what does this actually look like? Well, here's an example corpus, and I guess I was hungry at the time. I looked up the Wikipedia entry on bread, and here's an excerpt from it. And so if we were to use this document as our corpus, that is, as our stand-in for the English language, we're now asking the question, what word comes after the prefix the? Well, now we can just examine the document and find candidate words. So bread is one of the oldest, something starch extract from the roots of plants, the world's oldest evidence, so on and so on, the dawn, the Neolithic, the spread, the mainstay, the surface, right? Those are all the situations where the word the comes up. And so what I've done down here is collected candidate words that follow the word the in the corpus. So we have oldest, roots, world's dawn, Neolithic, spread, mainstay, and surface. So we will pick one at random, in this case, oldest one. So we'll say that the word that comes after the prefix is oldest. Cool. Now, repeat. Oldest is now the prefix, and we just answer the question again. If oldest is the prefix, what word comes next? Well, there's 2 times that oldest has appeared in this corpus, oldest prepared and oldest evidence, which means we have 2 candidate words to select from. So we'll pick one at random, evidence 1. Now, evidence is the new prefix, and once again, we'll go through the document, evidence from, evidence of, and we pick one at random, and so on. That's basically how this works. Here's a question. Given oldest as a prefix, what is the probability that we will randomly choose either of its candidate words? So here's a diagram of what we're looking at. We're starting with oldest, and we can either choose prepared or we can choose evidence. So what are the odds that we pick any one of these as an outcome if we're selecting them randomly?
50%. Since there's only 2.
50-50. Yeah, because there's only 2. So assuming that there's no dumb bias in it, and we'll just use your typical random number generator so we can assume that it's fair. So 50-50, yes. What about this? On is the prefix. There's 3 candidate words, on rocks, on a, and on the. What's the probability that we will choose any one of these candidate words?
33%.
Yeah, about 33.33, whatever. That's fine. We can just round it off. That's fine. So yeah, there's about a third chance that we'll pick any one of these. Here's a Monty Python quote. This came from a Python textbook, and they love quoting Monty Python over there because that's how Python got its name. So here's a Monty Python song about bees. I performed the same kind of analysis on that. Half A, half not, and half the. What's the probability that we will randomly select either of these words?
25, 25, 50.
Why?
Because the comes twice.
Yes. Yeah. So if you look in here, our candidate words are A, not, and the, but you're right. The comes in twice. So there's half A, half not, half the, and half the. The appears 2 times. The other words only appear once. So we're more likely to pick the word the than any of the other 2 words. Maybe you can see how this might work a little bit, because it seems like that if there are some candidate words that occur more frequently following a prefix, it's more likely that we're going to pick those than it is to pick other words that occur less frequently. So this is going to, and I think once we actually do the analysis and look at the results, you'll see how it kind of makes sense, and it reflects actual word usage and how people actually write in language. And so what it's going to do is sort of push our model a little bit over more towards writing the way people do, using the kind of words that people use, and sort of going down the same like writing paths that people do when they actually do writing. So here's what we're going to do, and we're just about to get into Colab in a moment, but I want to go over the process that we're going to go through. So there's a 2-step process. We have to get our data and prepare it for language modeling. And then we actually have to do the language modeling itself. So here is a excerpt from that Monty Python song again. So we'll just say that this is our textual data. We're going to pre-process it. We're going to make it lowercase. There's a lot of advantages to doing this. I'm going to kind of breeze over that, and if I'll have it addressed a bit later. I'll talk about this in a minute, but you're getting a little exercise sheet with things to try next if you want to. So, but for this demonstration, we'll lowercase the text. We'll remove non-alphanumeric characters because they are going to just kind of cause problems and make this more complicated, and so we'll just get rid of them. And then we'll do something called tokenization, which is there's a couple different ways we can do it, but the way that we're going to tokenize our document is to just split it by space character. And so what this is effectively going to do is take our input text and split it into individual words. And so what is along the bottom of the screen is what the textual data will look like once we are done pre-processing it. Once we have finished pre-processing, we're going to do something called a Markov analysis, where we are going to prepare a data structure that contains the result of that next character analysis that I demonstrated on the previous slides with bread, where we'll go through the document and compare every single pair of adjacent words like this, where in this case, half is the prefix and A is one of the candidates following A. And we'll add this to a table. In this case, we're going to use a Python dictionary data structure in order to make this association, where we're saying that the prefix half is followed by the word A. And then we'll move forward through the document. Now, A is the prefix, and the word B is a candidate. So A is now in the prefix column, and B is one of its candidates. And we'll go through the document incrementally, comparing every pair of words, every pair of adjacent words that we see, building up the table. At the moment, nothing is particularly interesting is going on, but I will point out what happens when we get here. Here, facto is a prefix and half is a candidate. So facto starts off there as a prefix, and then half becomes its candidate. When we go up here, half is now the prefix, and then not is a candidate word that follows it. But half was already in this table by the time we got to that point in the text of the analysis. So our prefix half has been followed by the words A, and then also not B, and so on. So if this text were our corpus, this table on the right is what the analysis dictionary would look like when we were finished with it. I suppose before I move on, any questions about this? Anything in chats?
Yeah, and actually, before we jump too far into the demo, we usually do a break an hour in, so maybe now would be a good time to take our little stretch break. But let's do some questions first, perhaps.
Yeah, we can do questions first and then break, and then we'll get into a coding demo.
Yeah, I did kind of have a question.
Okay.
Although it's a bit unrelated. Which IDE do you like for using AI in terms of like writing code? I've been using Cursor and it's amazing in my opinion, but I've also heard the good things about Klein, so I just wanted to hear what your general idea is about that.
IDE, I usually just use VS Code. Like what I write, I'm either writing code or I'm experimenting in notebooks, and it gives me both of those things. We're going to use Colab for this demonstration, so you'll
Yeah,
see
sure.
the notebook environment, but yeah, it's mostly just VS Code.
Gotcha.
Yeah, I saw a hand, I think it was Matthew. No,
Matthew,
okay.
you're muted if you are now speaking. I saw the hand go down.
No, okay.
There was a hand up. Don't be shy now, y'all. Or maybe your audio is broken. Michael.
Michael.
Muted. Michael, you're muted. Oh, here you go.
Yeah.
I'm sorry. As you talk about it more and more, though, I am starting to see why language models take so much data to predict what to say. I would imagine you would need tons and tons and tons of data to sort through all of the different variations of the language that is trying to process. So
Yes, we're going to touch on that a bit later, actually, because there's a really important concept we'll talk about in the second iteration of this that is related to ChatGPT's context window. That is how many words it considers as context when predicting the next word. Our example is only going to look at 1 and 2, which is peanuts. ChatGPT can look at the past, like, I think if tens of thousands, if not hundreds of thousands of characters. So yeah, it considers a lot of context when predicting the next word. And we'll very briefly talk about how it does that in a kind of hand wavy sort of way. But also I did prepare a list of exercises for you. So if anybody wants to like play around with this some more, there is a document that you should be able to get through Chris that gives you a couple targeted things to try. And some of them sort of plays around with that idea of how much context to consider. I see Santi.
So thank you so much for doing this. This is fascinating. I guess what I'm trying to wrap my head around, because I had heard that AI is basically the text predictive tool on steroids, and we're looking at how it might analyze a given text. You have probabilities, and then it chooses one per random based on how often they appear. But if randomness is at the root of it all, in those cases, how do we go from that to getting a response that is so cohesive? Because yeah, that's what I'm struggling with.
Yes. Part of it is that, well, that's the question, isn't it? Because modern language models have an element of randomness. In fact, it is necessary for it to have an element of randomness, because if it did not have randomness, it would ultimately just regurgitate what it was given as training without any, so in fact, the randomness is vital for how they work. How it applies randomness is a little bit different, and it might be more useful to talk about this again once we're done coding the model, because you'll have a little bit more like just texture for understanding it. But yeah, it's the short answer is that those models have a parameter called temperature, which is I'm sure some of you maybe have heard of it. I think they might expose it in the API, but ultimately, like, it is a parameter that controls how often it will pick So usually it just picks the most likely next word. Like it's not necessarily random. And actually I have a thing in the exercise sheet that will get you to do that with this model. But sometimes it will randomly pick a less likely word, and the temperature controls how often it does that. So if your temperature is set to 0, never pick anything random. It just regurgitates things that it's seen before. Temperature of a small number, it actually produces reasonable text. Temperature too high, it just nonsense.
Fascinating.
Yeah, but the randomness is extremely important.
Thank you.
Yes. Michael again.
To follow up on Santi,
Yes.
you said temperature controls the randomness.
Yes.
So is that why ChatGPT and other AIs tend to hallucinate when you give it too much?
No. I mean, I'm gonna make a fairly. It's not a bold statement, but it's a statement. So here we go. All language model output is a hallucination. Or rather, I don't think the term. I think the term is misleading. Because when we think of hallucination in a human experience, it tends to be that you are seeing things that aren't there, and there's a reason why, right? Like maybe there's a substance or something's going on in your brain. It's just in a state that causes it to diverge from reality. And so I think it carries with it the assumption that a hallucinating language model is in a weird state. In the same way that it would be if people were doing, but it's not. It's just carrying out this exact process that we saw here, where it's just picking the next word. And there's
Gotcha.
no internal difference between a hallucination and just producing regular text. So in a sense, it's all a hallucination. There's just an extent to which its output lines up with reality. And if it doesn't, it's just the result of this process that we see here.
And I mean,
Um,
I guess, in that same sense, human thoughts are also all hallucinations, or they're also all not hallucinations. You really
It
think about
depends on how you want to think about thought, because if you think of human thought as being, I'm going to pseudo randomly, let's say, pick the next word that comes next with no intention, then sure, it's the same thing. But you're now we're getting into much deeper philosophical questions about like thought and cognition and language, and we don't have time for that. So um,
It- a follow-up question though is, are there schools of philosophy that are followed more than others, like Kant and his understanding of reason, and like what guides the philosophy behind these models? Because we're wrestling with philosophical questions, and I'm sure you have to do that as well when creating different models. So
it's the fundamental loop, let's say, is just based on generating text that looks like the kind of text you've seen before. There's no underlying philosophy. It's just that's the mechanics of what happens and how it works. If these models have massive amounts of weights associated with them, so like we're not going to get into this, but neural networks are fundamentally just large linear calculations using linear algebra with by multiplying input vectors with these massive banks of just more vectors that are learned. And it tends to be that there are so many of them that you tend to start speculating like, well, is there some like kind of magic going on in the numbers that are selected and the kinds of like transformations that are taking place there? And unfortunately, that's the part of machine learning where you can't understand what it's doing. So so that's the part where I just have to be like, I don't know. Nobody knows.
Hand
But it's
waving.
interesting seeing people trying to pick it apart. Yeah. Um,
thank you.
Any other questions or additional comments?
No,
I know
this
we
is
have,
just fascinating. Wow.
yeah, we have some folks who thought a lot about data on this call. So if you want to add any context, that's cool too.
wait, what's the context? What?
Just kind of, you know, this is my attempt at a vague prompt at starting a discussion. It's Monday morning. Sorry.
Oh, yes.
Okay, well, if we're out of questions, then I think let's take a 10-minute break and we'll reconvene at 10:05. Sound good to everyone? All right, well, we'll see you in a few. You can use the I'm away react to unaway later and let us know that you're back. See y'all again.
Okay. Share my screen again. Okay. So here is what we're going to do now. So Chris has some materials that we're going to make use of. And so for our corpus, we're going to use Frankenstein, the sci-fi horror novel by Mary Shelley. So if you would like to follow along, you can get a copy of it from Chris. Otherwise, we'll just get into it. So just to look at this for a moment, just to look at the file. There's a great website called Project Gutenberg. There's a link to it in the follow-up exercises sheet that I had Chris sent around, so you can go check it out. If you're not familiar, it's great. There's a ton of old public domain books there. And if you are interested in language modeling or other language-related tasks from a machine learning perspective, it's a great resource because you can just download them all in plain text format and then do whatever you want with them. And so we're going to take advantage of that today. So this is Frankenstein. Nothing fancy. I just got it in a plain text format, so no style to deal with or anything like that. And so it's about what you would expect from a plain text file. Not going to scroll through the whole thing, but you see what I mean, right? Like it's just plain text, split across multiple lines. And so this would be something very easy for us to both load and interact with. So getting it back to the notebook environment. So this is one of the.
Sorry,
I'm sorry.
Did you get it from Project Gutenberg?
I did get it from Project Gutenberg, but there's a cleaned up version of it from Chris.
Yeah, I just shared it over to
Amazing.
everyone
Yeah.
on Google Drive. And Matt, I'm gonna actually share it to you as well, so
Oh, okay. So I can. Yes.
everybody can use the same thing.
Yes.
Yeah, good on you for using public domain text for this. That's
Yes.
amazing.
Well, it's a great resource. It's going to make the language model a little Victorian, I guess, but that's just what the data we have to work with here. So yeah, so we're getting into a slight disadvantage of Colab in particular. So we're working with Python in an executable environment that's presented by Google. The one downside to it is that unless you pay for it, any files that you upload to it to work with it will disappear once you leave a session. So if you're going to rely on Colab to do coding, what I'm about to show you, you'll have to do every time you interact with it. If you're doing it locally in your own setup, obviously that's not the case. But this Colab environment, like I said, is being run by Google. So we need to upload a copy of Frankenstein into an area where we can interact with inside of Colab. So if you have a Colab setup going already and you've downloaded frankenstein.txt, we'll click on this tab, and this is a set of files that's available to us in the Colab environment, and there's nothing there at the moment. So what I'm going to do is take my copy of Frankenstein and upload it here.
Yeah, and you can also just click the drive button, right? And use the file I just shared out.
Yeah, yeah, there's a lot of different ways you can upload it, but let's see. But ultimately you need to get it in there so it's available for use somehow. And let me see, did it not upload? Yeah, okay, there we go. There it is. All right, so there's frankenstein.txt. I uploaded it. It gave us a little warning about that. So it's basically saying like, hey, once this session is over, frankenstein.txt will disappear. No big deal, just upload it again. There's other ways of getting files into Colab, but this is the simplest one to show without getting into too much detail. So that's what we'll do.
Just to make sure everybody can follow along. If anybody not got that loaded yet, I shared it on Google Drive. So you might just be able to click Mount Drive, that little folder with a triangle, and then
I'm still working on that. 1 second. I've got to go to my email to see it, I think.
well, you should, if you just go to that little folder with the triangle on Matt's screen, then it should be, it'll ask you for permission, and then you say, then you just go to your shared files. You just navigate through there. Shared with me, I think.
Yeah, I don't really see what.
Okay, tell you what, I'm gonna just drop it into the chat. Does that make it easy for everybody?
I have I found your email where you shared me the text file, but I don't see the folder.
Okay.
Okay, so download.
Yeah, I guess it's not making a folder for, okay, here it is as a file on Zoom. And since this is public domain, we can share it as much as we want.
Yep, that's right.
Get it? Okay.
Yeah, by the way, I'm like the guy to talk to about the public domain in here. That's like my main hobby, so that's like my
Well, see, this is an example of where it's useful. You end up, there's a lot. In fact, I would not be surprised if ChatGPT was at least partly trained on data from Project Gutenberg. It shows up in a lot of machine learning data sets, and it's great if you're learning too, just because it's easy to get access to them. So I'll just assume that we have it all uploaded for now. And so I'll just walk through a little bit of the, actually, before we get into this, does anyone feel like they're not particularly comfortable with Python? Maybe quick show of hands if anyone is maybe not super familiar with it. Okay, we got a couple. I guess I apologize in advance. I will go through it and we'll examine what I'm doing and look at the outputs. That's one of the advantages of programming in an environment like this. But if you get lost to the point that you feel like you can't follow along anymore, we will share the code with you afterwards, and you might have more success doing it at your own pace. I don't know. So anyway. So I guess let's see here. So we'll close this, and I will create a code cell. So there's two types of cells in Colab and this kind of notebook environment: a code cell and a text cell. We won't look at text cells. Text cells are just there for presentation purposes. But let's take a look at this file as a whole. To open a file in Python, we use the open function, frankenstein.txt, and I'm going to do it in a construct that allows us to kind of safely open and close the file. So I'll do with open frankenstein.txt as in file, and then anything inside of this indented block will have access to the frankenstein.txt file, as long as it's indented over, we'll be able to use it. And so just to give a starting point, let me iterate through the file. What this is going to do is have Python load the file line by line and print the output. So we'll do for line in file print line. We'll see the output from this is, there we go. So this is the full text of Frankenstein printed out line by line. And so this is our starting point, essentially, just to start cleaning up the text and getting it ready for performing the analysis.
Yeah, and one little quick tip, when you finish writing a little block in Jupyter Notebook, you can use Control-Enter to run that block.
Yes, or you can click on the play button here. Easier to do Control-Enter, but yeah, there's a couple different ways you can run it, and then you'll see the output below. So there are a couple of things that we need to do to clean this up. One thing that is definitely the case here, and it's very often the case with text, is it might have extra space characters at the beginning and the end. Maybe if you've done web development work, you might have done this already, and some of you might know what's coming, but there's a function called strip, which just removes any extraneous blank spaces at the beginning and ending of the lines. And we'll notice something different about the text after we run this. What changed? There's no gaps between the lines anymore. Yeah, and so that's because all of these lines ended with the new line character, \n. Yes, so this is just remove that, and then if there are any extraneous extra spaces, they're gone now as well. So if we go back to the slides and we look at the pre-processing steps that I was intending to carry out, these are the ones that I want to do. We want to lowercase it, remove non-alphanumeric characters, and then split into individual words. So that's the goal. So if we go back in here, lowercasing is also a pretty easy thing to do. We can just print out the lower, or we can just call the lower method that's attached to all string functions. And if we run this again, we'll see it's the book again, but now it's entirely lowercase. There are no uppercase words anywhere in here. And then for a last pre-processing step, I want to remove everything that is not a numeric character, or sorry, an alphabetical character. So in this case, fear not. So I'd like to get rid of this quotation mark. It is going to get a little sloppy, and exploring better pre-processing techniques is one of the exercises I'm going to give you later. But in this case, mans will just remove the apostrophe. There are some advantages to doing this. It's going to make the analysis a little bit simpler, but it will have some weird effects on the output text. So there are a couple of ways that I can do this. I'm just going to do it with regular expressions. What's that thing they say about regular expressions? You have a problem, solve it with regular expressions. Now you have two problems. So we're going to do re.sub, and I'm going to say I would like everything but everything that is not a alphabetical character. Spaces are cool too. Okay, there we go. So all I've really done is I've taken the input text, removed extraneous spaces, lowercased it, and then removed everything that was not a space or A to Z. So numbers are gone, quotation marks are gone, anything other than A to Z and space. So that's where we are. Now, the next thing that we need to do is tokenize the document. That is, right now we're looking at entire strings. So this line right here, he spoke this with a voice so modulated to the different feelings expressed. That right there is an entire string, right? So that is a string that contains the words he, space, spoke, space, this, space, with, space, and so on. And what I would like to do is break this up into multiple smaller strings where each string is just a word. And we'll say that that's our token for the purposes of machine learning. So there is another Python function that's associated with strings called split. And if I call split with no arguments like this, it will just automatically do it based on space characters. So if we run this one more time, we now see that we've gotten what I wanted. And I'll go back up here. Here we have the document pre-processed, lowercase, anything but alphabetical characters removed, extraneous spaces removed, and now it has also been tokenized, where each word is its own string. And what we have here are just multiple lists of strings. I guess that would be the equivalent of an array of strings in some other programming languages.
Yeah. And I've got the final version of the code in the chat if you want to just copy that out for convenience, so you don't have to catch up.
That's all that tokenization is? That's wild.
It's a little more, we can go with more complicated tokenization methods if we want, and I've recommended one on the follow-up sheet. But if what we're doing here is word tokenization, and we're making the incredibly naive assumption that the boundary of words is at spaces. This is not always true. And if you want to think about why tokenization itself is such a complicated problem, think about languages like Chinese, which actually doesn't use space characters between words, and multiple characters can make up a word, or a single character can make up a word, and you just have to know the language in order to know the boundaries between words. It's very complicated. If we were speaking, if we were Chinese here, then it would be much more complicated to do this tokenization process. But English uses space as a means of differentiating words, and it's usually pretty reliable about that. So we can take advantage of that. So one last practical consideration. These are all just separate lists of tokens, and I'd like to just combine them all into a single list that just contains every single word in the document in order. So I'm just going to make a separate variable up here, words equals an empty array. And instead of printing this out, I'm just going to say words.extend all of the tokens that we get in. So all this is going to do is just result in one single massive list that contains all of the tokens individually. So that's what the extend function is doing. It's just saying like, hey, put all of these strings inside of the words list. And we'll run this. We don't get any output, but if I go down here and I type words, we can now see that we have each word in the text of Frankenstein in order of usage. And there we go. And now we're getting to the point where it's hard to show this on screen, but this is what we got. So now we have accomplished this. And what we have in code is equivalent to this. I'll go back to the notebook in a moment. Now what we need to do is carry out the process of Markov analysis. And so the first problem that we need to do is iterate through this list of words with pairs of adjacent words being the prefix and then a candidate. And we need to go through this process. And so we'll do this in 2 steps. First off, we'll just loop through the list so that we can isolate pairs of words, just so that we can have access to them. And then we'll worry about assembling the analysis dictionary. So we'll go back to the document. And so this is kind of maybe not a, okay. Anyone who's a little familiar with Python want to take a stab at how we're going to do this? I think I saw, did I see it? Oh, okay. Michael, did you raise your hand?
I'm familiar, but I don't want to take a stab at it.
Okay. Well, let's start off, right? Because if we wanted to iterate just through each word in the words list, that's pretty easy to do. We can just do for word
and word,
and then print word, and then we'll get output that is similar to what we had before. It's just not showing us the entire data structure again. What about pairs of adjacent words? There's a few ways we can do it. There's the clever clever Python sort of way, and there's also a much more simple way that we can do it with.
Could you use a list expression?
We could use sort of a, there's a specific function that I'm thinking of, but just to illustrate the point, words 0, words 1, right? This is a pair of words. And so in the terminology we established in the talk, letter is the prefix and 2 is a candidate word, right? And so then if I wanted to move forward by 1, I would say words 1, words 2, and now 2 is the prefix and this is the candidate word, right? So we just sort of need to loop through it in a way that we get access to them like this.
For variable 1, variable 2 in, I want to say enumerate.
Zip. Okay, so here's what we're going to do. I'm just going to write this, but I might actually do it in a slightly different way in case you're not as familiar with Python loops. We can do for I in range length words. And then we can do words I plus 1, right? This is a possibility. I think this is going to crash when we try and do it. And the reason why is that I actually need to do -1 at the end for the length because we don't want to go past the end. But I think you'll see that this works and does what I want. So we have like discovered that I made notes concerning his. So discovered that I made notes concerning his history. So this has solved the problem. Another more clever way of solving it is for prefix candidate and zip words. This is also another way of solving the same problem. So we see remorse will not cease to rankle, so on and so on. So we got the same output. This is a little bit more like cleverly Pythonic. This one is a little bit more just traditional programming. You would see this kind of thing in any particular exercise. Given that I don't know if we have a huge preference for how this is going to work, I'll just I'll use this one. The zip approach is in the notebook that's being circulated around. So we'll have a couple different methods of doing this that we can interact with. But here's what I'll say. Prefix equals words at I, candidate equals words I plus 1. And so now we have our prefix and our candidate. And so now the idea is that we need to build up a, what's the data structure here? Dictionary, yes, that's right. So for those of you who aren't familiar, dictionaries are an associative data type. They're like objects in JavaScript, and they're like maps, just in a more formal data structures type of way. So I can do something like this, and I can say A is associated with 1, B is associated with 2, right? Something like that. So my Dictionary equals this, and then I can look things up by the key, and I can get the associated value. So in this case, I made a dictionary where the string A is associated with the number 1, the string B is associated with the number 2, and I can go in and say, hey, what is associated with A? And then I got back this one here. So to build a structure that looks like this, we can have a string as the key of a dictionary here. How are we going to account for the candidates over here, considering that at least in one case in this example that we looked at, there's 2 candidate words? So we need a way of structuring the dictionary where a single prefix can be associated with an arbitrary number of candidates.
Any ideas? Anybody tried anything like this in Python before?
Could you put another dictionary or a list?
I think a list is the right approach. So to reproduce this, let's see what this would look like. So half A and not. So it would look like half and A. Right. I think that's that makes sense. I think this would be a good way to approach it. And so that way, if our prefix was half, we would see that all candidate words associated with half are, in this case, these 2 options, right? So we see how we could get something like this if this was our input sentence. So what that means is that we're going to need to do a couple of things. We're going to do analysis equals a dictionary, and you can do it by either calling the dictionary function like this or just giving it a curly braces like this. So what do we need to do if we've never encountered this prefix before and we want to add it to the analysis dictionary? If prefix not in analysis, what happens if we're encountering a brand new prefix that we've never encountered before? We need to make an empty list to make room for the candidate word that we're about to add to it. And then if we have encountered it before, or we just did this line, we'll say analysis prefix dot append candidate. And that is all. That is the entirety of our analysis.
This is a super common pattern that I've used over and over for building an associative, data store with multiple possible things. It's useful for how many times have I seen X, or just kind of collecting things under that one key association. So I'll paste this into the chat. I'm going to paste something equivalent that uses a slightly different method, but.
So if we're actually it's done running already. Again, we're just working with one book here. If we were dealing with a lot of text, we might have a bit more time to wait, but analysis, and we'll actually look at it. So let's see, what do we have here? So this is actually pretty good. So it looks like, according to this, and this is too big to display the entire thing, but I would recommend just navigating around it on your own and just seeing what associations it was able to pick up. So it looks like for the prefix 2, the number 2, lots of candidate words. So we have stiff, o'clock, hours, days, years. And in fact, it looks like years is quite common in Frankenstein. It seems like they talk about 2 years very often in the book, whereas brothers doesn't occur very often. Months, excellent. There's a few options here, it looks like, but it seems like just a rough analysis of this, if we were to choose the word 2 as a prefix, it seems pretty likely that we would choose years to come afterwards. And it seems like it would not be very likely for us to say, I don't know, 2 excellent. That only appears once. Here's another one. So accidents, which of winter, might, and have. So it seems like every time they use the word accidents, these are all of the times that it was used in the entire book. There's only 3, 4, 5 candidate words, and each one only appears once. So there's only 5 options here, and they're all equally likely to be chosen. Here's a few with only 1. So leak was only used once in the entire book, and it was immediately followed by the word are. So only 1 choice there. And so you'll typically see this if you go through this dictionary, you'll see a lot of examples of some words that are used very frequently, and you get lots of candidate words, some words which are used very infrequently, and so they'll only have maybe 1, 2, 3 candidate words, something like that.
Chris, could you copy and provide the code again?
Yeah, I just saw the
Thank you.
error Billy posted. Let's see. What did I miss?
Let's see if I mistyped something. I must have.
Just
I guess
try
I did.
copying.
Oh, it's
Well,
it's the length of words -1.
Yeah, and you have analysis as a list instead of a curly
Dictionary,
braces.
yeah.
All right, let's try it now. Another one. Okay, let's see.
Yeah, let's maybe take a moment
Length
here
was
and try and
-1,
all
okay.
catch up.
Yeah, let me make it so that everything is on screen.
Yeah,
All right,
and if
cool.
you-
That actually appeared to work.
Cool. Anybody else need to catch up? There's if you look at the 2 blocks I've posted, I think you can copy them from the text, like the little code box has a little copy button on it, and it messes up the indentation in my chat window, but so make sure that you yeah, it looks like my editor decided to 2 space on one and 4 space on the other, but sorry.
I got it.
This is insane. I love this.
Yeah, this is cool.
Oh, we're only halfway done, because now what we need to do is use this analysis dictionary to generate text. And that's the next important part, because we've been hand waving that away for the most part, because we've just been assuming that a prefix is available. But what I would like to do is 2 things. One, we'll randomly decide on a prefix, and then we'll go through the process of generating text from that prefix. That's just the best thing to do in this situation. Once it's over, we can maybe talk about how we're doing far more randomness than ChatGPT is and how it determines a prefix, but still, yeah, like we got to pick something, right? So let me import the random module, because we are going to need to make some random choices here. So we'll have that available. And if you're not familiar with the notebook environment, all you have to do is run this cell again, and then you don't have to run any of the intermediary cells anymore. Random is just now part of the script, and it's available to you. So we'll go down here. So let's take a look at, well, okay, so when we do a dictionary, what we have are keys and values, right? And we've already established in this dictionary that the keys of the dictionaries are single strings. So the key is the prefix, and the values are all going to be lists of candidate words. And Python exposes the keys of the dictionary like this. We can just call the keys method that is attached to all dictionary objects. And what we'll get is a slightly annoying list-like object, I'll say, that contains all of the prefixes in the book Frankenstein in whatever order they were. I believe it's just whatever order they were added in the dictionary. This is not a list, and this is going to be slightly annoying. We actually need to convert it to a list. This is just a language consideration. Python requires us to do this. We'll do this, and it looks slightly different. This is just how it outputs lists. But the whole point is now we have a list that contains every prefix in the analysis dictionary. And now that we have one, we can call random.choice and pick one at random. So all we're going to do is, well, anytime I run this function, it will just pick some random prefix from the dictionary. And we can say that this is our new prefix. If I print it out like that, okay, vicious. Vicious is our starting prefix. Given that prefix, let's see what our options are. So we'll go back to the analysis dictionary and use the prefix as the key. And it looks like if vicious is our prefix, we now have 3 possible candidate words to choose from, and as or motivates. So if we want to pick our next word, hey, that's easy. All we have to do is random.choice, and we'll pick one of them at random, and it looks like vicious, and that's going to be our choice. Let's kind of look at a few more just to get a little bit more texture for this. I'll pick another prefix. Decision. Okay, let's look at all of the candidates for decision. Okay, of and which. That's not very interesting. Mutilated. Oof. One. Okay, so that appeared once. Really, just once? This is a horror book. What is this? Come on, Mary Shelley. What are you doing? Peculiarly. Okay. Oh, here's an interesting one, right? So this is an example of one where there's a word that's more likely to appear in the output. It seems like if peculiarly is our prefix, we're more likely to pick fortunate as the follow-up word, just because that appears twice, and then the rest of them only appear once. Maybe let's do one more. Consolation. Ooh, this is a good one. A lot of different options. Doesn't look like anyone is particularly more likely than the others. I don't know. We'll just pick this as our starting point because I got to stop here somewhere. But I do recommend playing around with this a little bit more and seeing what you get. It'll give you a better idea of just what's happening internally when we do the model. So here's what I'll do. The choice of the analyses. So we got consolation I, right? So our choice is random.choice this. So we have a prefix and we have a choice. So what we did was we started with consolation. Oh, did I run it again? I think I did. Yes, I ran it again. We randomly picked a different one. Consolation, and then the choice that we made is Elizabeth. I'll do this one more time. So prefix is horrors, choice is of. So our prefix was horrors in this case, and then the word that we produce is of. So we're making progress, and now we just have to do this a lot of times. Let's decide how many. Actually, what am I going to do? So we got our prefix, got our choice. So here's what I'm going to do. I'm going to say for underscore. This is just a Python convention, meaning I don't care about the variable in range 10. So we'll generate 10 words. Choice equals random.choice analysis prefix. What happens after we make the choice? What do we do after we make the choice? That becomes the new prefix, doesn't it?
We make another choice?
Yeah, we have to do this 10 times. We're going to generate 10 words of text. So we start with our prefix. We use the prefix to choose a new word. And then that word that we chose now becomes the new prefix. And we just do this over and over and over again. So here's our output. Unknown to me with the theory, and I believed in so. Fade away in wretchedness, yet in which I cleared away and. Crawled into a considerable difficulty, sit upright, mind unfolding as you. Soften feelings of the diffidence of August, my bedroom was. That's an artifact of bad pre-processing, I bet. Quick pace is something in the wonderful and if in the. Not great, but it is textual output, and we have now completed the algorithm and made it work. One last thing that I'd like to do is actually make this into a nice sentence. So I'll do sentence equals a list. We'll choose prefix, sentence.append prefix, sentence.append choice. And then instead of printing it as we go along, I'll just print in. Yes, okay. So all I've done here is just put all of our choices into this sentence list, and then I join it together into so I undo the tokenization, combine it down into a single string at the end, and this is our output. So is this good? Is this bad? Maybe it's not as coherent as everybody was hoping it might be. A good question to ask is in machine learning. Very often there's no particular behavior that we're looking for. Instead, we're just looking to see how the model behaves and whether it's better or worse than a particular baseline. So a useful thing to do in this case might be to compare this with a baseline where we're not making any choices based on the structure of the document at all. We're just randomly picking words. If we gave that a try, well, let's see, we can do sentence and random.choice, analysis.keys, and I think I need to turn that into a list first. And then I'll do this here. And random.choice. Oh, convert it to a list first. Okay. So the idea here is that we're just going to randomly pick words from our analysis dictionary and look at what kind of sentence that produces and compare just total random selection with our model. So here we have Sicklin and Glorious, Madly, Beer, Reception, Seville, Execute, Recent, Insatiable Complaints. And here we have Internal Being was evening when he appeared dead at some person. Both completely nonsensical. But if you had to choose between these two sentences as to which was less nonsensical, what do we think?
Number 2.
I think so too. I
So
think
you're
the
getting to
language model
fine-tuning,
produced.
right?
What's that?
You're getting to fine-tuning? Is that what?
Well,
No?
no, we're not fine tuning. We're just comparing the model against random selection. So the idea is we're
Oh.
just picking words at random and we're seeing if our model seems like it's better than random choice. And I think it is. I think it outputs things that are slightly better than if we just randomly selected words from Frankenstein. I get little moments of coherence in this. If we were to do this over and over again, there's like words that seem like they belong together, whereas something like this with just randomly selecting words, this is just utter nonsense. And if it does produce anything which is readable or intelligible, I expect it would probably be primarily just by coincidence. Whereas this, if it produced something that seems intelligible, it's because it produced something that's based on an intelligible sentence that it saw previously. So I would say that this is a little bit better. But of course, in machine learning and in language models in particular, there's always the question of, can we do better? And in fact, we can. And there is a way that we can tune this model a little bit and improve its output that's a little bit clever, and maybe will just require a little bit of a leap of logic from what we talked about previously. And so here's what I would like to talk about with respect to that. So let's go back to our bread example. And I want to introduce a concept called n-grams. N-grams, where n is a variable and it's a positive integer. An n-gram is a contiguous sequence of n items taken from sequential data. That's it. So if we were to reframe our conception of the prefix at this moment, the prefix is a 1 gram or a unigram. That is to say, we take one item at a time from the corpus. So if we're looking at the prefix the oldest, the roots, the worlds, the Neolithic, the spread, etc., the is a 1 gram or a unigram. And one of the disadvantages of unigrams, as we can kind of see from this, is that it doesn't give us much context, right? We're only starting with the word the, and we are choosing from a list of possible candidate words that come from every single usage of the word the. But if you look at how the is used in the document, sometimes it's the first word in a sentence. Sometimes we have things like with the dawn and the spread became the mainstay. There's sort of an additional layer of context there that we're missing out on. And that means that of all of the possible words that we can choose from, we're sort of choosing a bunch of different candidates from a variety of different contexts. But the question is if we expand the context out from a single n, 1 gram, to 2 grams, that's going to change the prefix so that the prefix is no longer a single word. It is now 2 words. And in this case, 2 gram, bigram, both mean the same thing. We'll say that the prefix now consists of 2 contiguous words. And we'll see that the list of candidate words has shrunken substantially. And that is because there is now an additional word of context in the prefix. And so my expectation is that by using 2 grams instead of 1 grams, the analysis is going to become quite a bit more constrained because the context is more specific and we'll lose a lot of candidate words. But what that means is that of all the candidate words that we can choose from, they're going to be much more focused and specific to the bigram prefix, just because, again, there's an additional word of context. So the theory is that unigrams maybe will be a bit less coherent than bigrams, or to flip it around, if we use bigrams instead of unigrams, the text will be a little bit more coherent. So let's do a quick refactor of this, where instead of producing an analysis dictionary using a single prefix from a single word, we'll implement bigrams and see how that changes the analysis. So
Yeah,
I'm
and
going to
just before we go too far that direction for
Yes.
much, just want to check in with everybody. Is anybody not able, like, not keeping up? Anybody need help getting caught up to here, or have questions about anything we've covered so far?
I just think it's thematically appropriate that we're using Frankenstein as the text. Because not only is it one of the earliest science fiction stories, but it's also about cobbling together, all of these different pieces of a man into something that has intelligence and life. And I wonder if that was perhaps the reason why you picked that.
I just like it, but I do agree it's a bit more thematically on point than I thought originally. But yeah. So anything else before we move on to the refactor? Okay. So I'll have this down here as reference, but let's just go back to the words list as it is. This is what we're looking at now. So instead of letter being the prefix and to being the candidate word, we're going to have to reframe this just a little bit, where letter 2 is the prefix and Mrs. is the candidate word. To put it in Python data structures terminology, we could do this. Just to highlight this, in case you're not familiar with this, we're making tuples, which are just immutable lists, essentially. And so I've just grouped these together. Letter 2, in this case, is the prefix, and then Mrs. is the candidate word that comes next. And so we just have to modify this loop in order to support this. And there's a couple of things we need to change. We'll need to subtract 2 from the total, because if we don't, we'll crash at the very end, and we don't want that. Prefix, now we have 2 prefixes, so we'll have prefix 1, prefix 2 equals words I plus 1, and then the candidate will be words at I plus 2. We can construct the prefix as prefix 1, prefix 2. Again, we're just creating a tuple here, which in Python terminology is an immutable list. It has the property of being able to be used as dictionary keys, which is nice. So we've just assembled the final prefix piece of data from the 2 parts that we extracted from the text. So this is our bigram in this case. And then the rest of the code doesn't actually need to change in any capacity, because we've constructed the prefix as the 2 as an amalgamation of the 2 prefix parts of the bigram, and then the candidate is just the same as it ever was. So I think we can actually just run this and get the same result. Let's take a look at the new analysis dictionary and see how it's a little bit different. So let's see. Okay, here's a good example. So this has fundamentally changed the structure of the analysis dictionary. I mean, it's still the same. The keys are all prefixes, and the values on the other side are the associated candidate words. But we can see by adopting bigrams in this case, it has changed both the nature of the key and also the nature of the candidate words that we have up for selection. I think it's going to be a little difficult to compare them here, but I would say please explore the differences between the 2 data structures on your own. And in particular, I think what we see right here, where there are many bigram prefixes that are only associated with maybe like 1 or 2 candidate words, I expect that is going to be far more common in this analysis dictionary than with unigrams. Good exercise might be to prove it. Go in and actually count the average number of candidate words associated with each prefix in the unigram of the bigram model. But we still get a good example of different ones. So if our prefix is depart for, Our candidate words are the, and then ever. Oh, that's kind of funny. Depart for the tavern, or depart forever, as in like goodbye, I'm not coming back. That's kind of that's amusing how that worked out. The latter, fairly large number of candidate words. The latter town, the latter and, the latter should, the latter in. So things like this. You'll just see a variety of things like this. So this is our dictionary. So let's actually start generating words with this. And sorry, sentences with this. So let's do this. Random.choice analysis.keys. I think I need to make that a list structure again. So list. Okay. Same thing, right? We're just going to randomly choose a prefix. And the only thing that we need to contend with that we did not have to contend with this time is that the prefix is made of 2 parts. But functionally, still the same process. We're still randomly selecting a prefix from all of the prefixes in the analysis. And we can take advantage of Python destructuring to just break it out into 2 variables automatically. We can do this because it is a tuple and because it contains 2 parts. So I can just do it like this. And oops, I always hit that. It's very annoying. So I'm going to prefix 1, prefix 2, same output. So clapping my where this barred windows, whatever, that's our prefix. To see what candidate words are associated with this prefix, we can go back into the dictionary and just do analysis and look it up, just construct it back into a tuple. And so it looks like if our prefix is barred windows, we only have 1 choice. And if our prefix is nor known, our candidate word is nor. Exertion, but the, surely the, gentle spirit and spirits. Maybe you can kind of see from this that in general, we're seeing fewer options associated with each prefix, right? I think with the unigram analysis, there were more of them available. In this case, we're dealing with a more constrained set of possibilities afterwards. So we'll just go up and do this again. So let me just kind of work the code back for this. So we'll do prefix 1 and prefix 2. We'll make a loop. So for 10 choice equals choice 2. Okay, so I'll just do this just as a little bit of an exercise because there's one last little leap that we need to make in terms of the coding of this to make this work. I just had it iterate through 1 instance of the loop, and so we can see the output. So in this case, it across was the prefix, and then the was the candidate word that we chose. How do I restructure the prefix so that I can go back in and do another iteration of word selection? Because I can't just do prefix equals choice anymore because choice is just a single word. So what do I need to do to the individual components of the prefix to make this work?
Anyone?
I'm actually at a loss.
Gotta scoot him over.
Anybody need help catching up?
Sorry, what was the issue, the problem that we're facing again?
Oh, okay. So previously, when we made our choice, we just did this, right? We just said, okay, the prefix is now the thing that we just chose. But we can't do that anymore because our choice is a single word and the prefix is made of 2 parts. So how do we assemble a new prefix from the choice that we just made? We can't do this.
Is there a tuple that already exists that contains our choice, or or in other words, if we're making the prefix the choice now, or if we're making the choice the new prefix, could we? Is there a tuple? Would it be too much to like find the tuple that choice belongs to?
Well, Here's maybe an interesting point. I should bring this up. I think you're on the right track. We do need to restructure it from components of the original prefix, but let's go back to the half of the
Alisha?
example. Or yeah, okay.
We wanna,
The other week when we were doing Arcadas, would it not, I can't remember the name. Is it like bit shifting? What was it again? Like,
yes. Bit
with the-
shifting works really nicely for dividing by 2.
Yeah.
I see where you're going with
integers
this.
represented in binary.
Let's take a look at this, and I'll do half of the. I don't remember the lyrics to that song. So half of the
Half not
philosophic.
be.
Yeah. Okay. So this is our text, right?
Oh,
So
half be.
when we were looking at this, this is a prefix. I can't really do text like this, but in this case, half prefix, half candidate A, right? This is what it looked like with unigrams. Half was the prefix and A was the candidate. Now that we've expanded it to bigrams, half A is the prefix and B is the candidate. So this is the prefix half A and then B is the candidate word. If we were to select B and then move on, and remember, ask the question again, because we're doing this in a loop, the candidate becomes the new prefix, and then we ask the question again. What does it look like when we take this prefix and just slide it over by 1? It becomes AB, and then philosophically becomes the candidate word.
So you need to make a new tuple out of the prefix to and
Yes.
the choice.
Yeah, I wish I had if I had a blackboard, I would be pointing at it right now. But yeah, essentially what we're doing is we're sliding it over by 1. If it's half A and then we chose B, B now becomes part of the prefix. And since it is just a bigram, we get rid of half. And so just slide it over. That's what we're doing. So in fact, prefix 1 becomes, prefix 2 becomes prefix 1. Prefix 2 becomes choice. And that's it. Does everybody see how this happened and why we're doing this? Also, I see a hand up, Alisha.
Sorry, that must be old.
Oh, okay.
Zoom is really great on Linux, huh? Get it together, Zoom. We know you're listening.
So let's do sentence equals array. We'll sentence and prefix 1, sentence dot append prefix 2, and then inside the loop sentence dot append choice. And then we do this sliding operation where we just scoot everything involving the prefix over by 1. So again, the second part of the prefix, the second part of the bigram gets promoted to the first position, and then the choice now becomes the second part of the bigram. And there's our result. And if we do the destruction, shall I read and reread her letter? I will hover near. The wreck I perceived drew tears of gratitude at his acceptance, but rude
That was the best
abode
one yet.
fairer than a garden of roses in, also an artifact of pre-processing and the smiles of constellation, unbounded, unremitting attentions of my journey, my father's exertions apart. Still incoherent, but more coherent than what we had before.
That second one was like a full sentence though. Like it actually looked like something that could be real.
And I would say there are metrics that you can use to deal with intelligibility and things like that. But I would say if we were plotting this, excuse me, random choice would be 0, like just completely unintelligible, just completely random gibberish. Unigrams, better, but still lacking like a cohesiveness. And apparently all it took was to add 1 extra word of context, and we're now getting plausible sentences.
Yeah, I was going to say that as somebody who reads these older texts a lot, and I mean, I've been doing it a lot for years, this looks believable. Because, I mean, you have to, with some of these really old books, you have to really sit down and like think about what the guy's saying, or else it's going to look a lot like gibberish, you know?
Yeah.
because it doesn't translate well to modern speech at all. It's very overly formalized and whimsical and all this. So
Yeah.
it,
But like you can kind of see how what it outputs is wholly dependent on the way language is used in the text. So if you used a different text that was a different vibe, so instead of like, you know, the world, what is it? The world's first science fiction horror novel. You know, if you switched it to more modern book, it would look more modern. If you switched it to a stuffy reference book, it would read like a stuffy reference book. And so one of the exercises that I have on the sheet that Chris should have either handed out or will pass out involves like constructing a more complicated corpus from many books in Project Gutenberg and combining them and seeing what effect that has on model output. Yeah.
Michael?
So I would imagine certain like highly specialized language models would be trained on highly specialized books, right? Or data.
Yeah. So typically so actually in machine learning, there's this concept called fine tuning that you tend to see a lot. And what that means is that like something like ChatGPT is almost impossibly expensive to train. It can cost like hundreds of thousands, if not millions of dollars just to train it because it's so big and like this took seconds for us to do. And the amount that this cost is like negligible. But it can take so long, like it's both a monetary investment and a time investment as well. It can take weeks, sometimes even months to train, and it's extraordinarily expensive. So one thing that's very common to do in machine learning is to have a general purpose model that's just trained on a massive pile of text, just like everything, books, reference material, tweets, Reddit posts, chat logs, just like everything, and the kitchen sink. And then you fine tune it where you now have a very specific thing you want it to do. And so you have your own corpus of documents that is unique to your task. And then instead of spending like millions of dollars and months of your time training this whole model, you've got this model where that's already been done. And then you can spend much less time and much less money just kind of making it specialize on your smaller data set. We do that a lot. Yeah.
Just so you all know, the code I'm posting in chat is a little bit different format. I'm using prefix. I'm keeping like tracking prefix as a tuple, a two tuple, and then deconstructing it. So slightly different than Matt's approach, in case you noticed that it was different. But you should be able to copy my code blocks and then run them. Is everybody caught up to that point? To be able to generate a sentence.
yep.
Cool. So that's that demo. If we don't have any more questions, we're almost done. So I can just go ahead and jump back to the lecture, and then we could just have maybe an open discussion at the end and just do that until we run out of steam. So I have
Okay.
one last thing that I wanted to talk about, which is what makes, I'm picking on ChatGPT here, but any modern language model different from what we're doing. So I've been throwing the word context around a lot, and I think it's important to focus on that because that's actually what makes or breaks these models. And maybe you can kind of see already a limitation in this extremely simplistic approach to language modeling, which is that the amount of context that we have available to us when deciding future words is extremely limited. And in particular, since this is an n-gram-based model, the amount of context we have is n, right? If it's a 1 gram or a unigram, we have 1 word of context. If it's a bigram or a 2 gram, we have 2 words of context. Pick an n, right? 3, 10, 100, whatever. That's just how much context we have available to us in making our prediction. And you can probably see from this that bigrams offer us like double the context of a unigram, which is not trivial. That's a lot of additional context. But in this example here, you can see that of the entire document, that's still peanuts and doesn't really tell us anything about what, say, the document was trying to accomplish. Like I said, I got this from the Wikipedia article on bread, We know that it's about bread because the first word in the paragraph is the word bread. And so we can assume that that's what the document is about. But then in our bigram system, it only takes us a couple of steps before we've moved on. And we kind of just don't know that this is about bread anymore because we've lost that context. And by the time we get to this end here of flatbread, we're all just kind of like super far away from anything. And we're just ignoring all the rest of the document. And so while this can create little moments of coherence that looks like something somebody would have written, as we saw in the output, this is not enough to write a coherent document. And so this is fundamentally limited. What ChatGPT does, and other language models as well, is they're built using advanced machine learning techniques that can use an entire document as context. So when we do this, we pick a value of n for n-grams, and whatever that value of n is, that's our context window, right? That's how far we're looking back into the document, and we only have a limited context window of maybe like 2. ChatGPT still has a fixed context window. I think we just talked about that earlier in the talk, but it is so large that for all practical purposes, it might as well not exist. If you start getting into a situation where you hit that context limit, you're probably already running into other issues. I don't know if it's just me, but I've noticed ChatGPT gets really slow with long chats. And part of the reason why it might be getting so slow with long chats is because it's having to feed the entire document back into itself at each prediction that it makes. So that's a lot of network traffic, and that's a lot of computational resources. And so maybe that's why it's slow as it is. But yeah, this is what ChatGPT does. We look at the previous n words. ChatGPT looks at the entire document so far. But even so, it's still answering that same fundamental question that we are, which is, given all of this, what's the next word? Actually, it's not even word. There's a different tokenization system they use, but that's outside of the scope of this chat. We'll just say it's words just to make this easier to deal with. So you might be asking yourself, oh yeah, do we have a question?
Just to see if I understand you correctly. So, like you said, when you're in a chat and with Chat GPT and it goes on
Yeah.
for too long, it starts to get slow. Is it reading the entire, like every question that you've asked it, going as
Yes.
far down to the bottom? That is insane.
Yep.
Oh, wow.
Sure is.
Well, and when did anybody use ChatGPT prior to its like having that context? Like maybe what was it, 3, ChatGPT 3? Like you could ask it something and it would get something wrong, and then you're like, oh, actually, what I said before, use that as context, and it will just create a new response based on, that one prompt, as if it had no memory, because it didn't. It's just doing it was just constructing, a response based on the immediate prompt. It's only recently that they've started to kind of keep that context. Well, I guess it's been a while now, but they've started to keep that context and feed it back in so that it seems like it has some memory or knowledge of what you've been talking about and can build on it.
Yeah,
Yeah.
but to be specific about that, because I've been using ChatGPT for a long time too, and I recently switched to Claude because of this, and I'm not loving ChatGPT much anymore. I love Claude. Holy cow, it's so good. But basically what ChatGPT has is a certain limit. So you know how our limit was n equals 2, right?
Yeah.
Well, its limit is like, I think like 100,000 words or something per context window. So if you start
Yeah. Oh,
going
Claude
down,
has a higher window, doesn't it?
Claude has a insanely high window, but like, I mean, you can give it a 500-page book and it will accurately parse stuff out of it. That's like it's around its limit is around 500 pages, and that's like insane.
Yeah.
Because ChatGPT 4.0 will only do 40 pages. Because I
Wow, okay.
specifically enter in books to talk about them with LLMs, and Claude wins with flying colors on that because they
Yeah.
you can give ChatGPT a whole movie script, but it's but yeah, so like what happens, what you're talking about there is it's not really, at least I think, it's not really quote unquote remembering it as like a conscious thing. It's like okay, the last three things we talked about are now context, but it can only do that for so long. So if you talk to ChatGPT for like hours, you'll start to notice, wait a minute, you forgot the stuff we talked
Yeah.
about at the beginning of
Yep.
the conversation.
Yeah.
And then
Yep.
that's
And
because
this is why.
it only has context. And you could probably go for days talking to Claude, I would think, and that won't happen.
Yeah. And it's all just a generalization of n-grams. Like fundamentally, it's not really any different than what we're doing here. It's just the system for consuming and making predictions about the upcoming word is more complicated. But you could describe the context window as a sort of n-gram. And so in the same way that we expanded our context window from 1 grams to 2 grams, ChatGPT is just doing that, but expanding the 2 grams to 100,000 grams or whatever. But the question that it is asking is still fundamentally the same. And that whole sliding over behavior that we saw with 2 grams is still fundamentally what it's doing once it reaches the end of the context window. But how does it do it? Because when we did ours, it's a lookup table, right? This is what our language model looks like. Given a prefix, we literally go look up the prefix in essentially a table. It's a dictionary, but we could say it's a table. And we just literally look up a list of candidate words that follow, and then we make our choice based off of that. But I don't think that could possibly work with ChatGPT, right? If it's using your entire document or close enough that it doesn't make any difference as context. Maybe nobody has ever written that specific sequence of words before. Maybe people have written similar things. But if it has not written that specific sequence of words before, and you don't have that specific sequence of words in your lookup table, then the language model can't possibly function. So how does ChatGPT get over that? And this is the difference between our approach, which is machine learning, by the way. We have done a machine learning exercise. It's a very simple one, but it is still machine learning because our computer learned from data, right? Still machine learning, just simplistic. The kind of machine learning that ChatGPT uses is much more big and complicated and uses neural networks, essentially, that are able to do this kind of thing. And so here's some very brief, short, quick intuition for how it works. And it's based off an idea of something called word embeddings. And by the way, this is a huge generalization. This is not necessarily how ChatGPT specifically works. I actually based this off of a much older style of neural network that is not used as often anymore. But in principle, what I'm about to explain is similar to what ChatGPT does. So this is not a literal description. It's just here for intuition, just so you might get a sense of how it works. So the idea behind word embeddings is that they are vectors that represent words. And you might ask yourself, how can a vector represent a word? Well, that's a great question. What you can do is train models that capture the essence of the word in a numerical representation. Now, what each of these numbers mean, we don't really know. We can't figure out except through what's called a post hoc analysis. That is, we get these embeddings, we see that they've been trained in a particular way, and we can look and try and find associations between certain values in here and different types of words. Maybe this particular number right here is associated with, or no, let's say this particular number right here is associated with the carbohydratiness of whatever the word is. And so it's very high for bread. And it's low for most of the other words because they don't really have anything to do with carbohydrates. I don't know. That's the point. We don't know exactly what these numbers are, but they are discovered essentially by a neural network such that they are maximally useful for working with individual words. And so what you can do is you can take a word embedding, that is, that say the vector associated with that word, as a kind of stand-in for the word. And even though you don't know what each of the numbers mean, internally within the model, they do mean something and they are relevant to maybe differentiating the words from one another, or sort of understanding what's unique and what's different or what's special or how a particular word is used. So you're just going to have to trust me that each of these vectors that I've put on the screen is in some extremely abstract sense related to the meaning of a word or related to the way a word is typically used. Once we've represented words like numbers like this, or once we've represented words as numbers like this, then we can do all sorts of fun stuff with them. And in an extremely hand-wavy gesture, I'm just going to say that we'll get a neural network, look at each of these numeric representations of words, and output another numeric representation that, again, we don't really know what it is or what each of these individual numbers mean, but what we can assume is that numerical representation is in some way a summary of the sentence collected so far in a way that maximizes the ability of the model to predict the next word. So the whole point behind this is that a neural network is looking at these numeric representations of these words and summing them up in a way where the output is, say, very close in a literal spatial kind of Euclidean space sort of sense to the numeric representation of the best next word. So bread is one of the oldest. Prepared would be the reasonable next word to come up with. And you'll notice in this example, the contents of the vector for the prepared word is pretty close to the numeric representation output by the neural network. So it can look over an arbitrarily long context window because the neural network knows how to take a sequence of word embeddings or word vectors like what you see here and summarize them together in a way that allows it to predict the upcoming word. So it doesn't matter how long the context window is. It could be very long, it could be very short. Either way, the summarization process is the same, and it's something that the model just learns how to do from looking at many documents. And to be clear, the process of summing up the words, the actual contents of the word embeddings themselves, and this distance between the output and the actual correct option is all learned. We don't know any of this stuff in advance. It's just learned, and the values that it settles on are the values that were just most useful for it to make this prediction. And that is basically how it works. A lot of hand-wavy stuff there, but essentially that's what's going on. You represent words as vectors of numbers. You do some neural network stuff on those numbers. You get some kind of output that helps point you in the right direction towards what the next word is. And that's it. So I
Yeah,
guess we
so
got about...
hopefully all of this demystifies language models a little bit.
And also possibly mystifies it a bit more because it got a little hand wavy near the end there. But that's basically how they work.
Just say hyperparameter tuning.
Yeah. So I guess we could do a brief discussion or questions or whatever.
Yeah. Questions, comments, anybody not able to get to the end of the interactive demo? Anybody need to catch up or anything like that? Don't be shy.
I just thought it was cool. It's fun seeing where the actual, because my understanding was that there's a lot of the training like happens, that they program the trainer and then they program the random, like essentially like what we just did where we actually like program the random tokenization part. And it's fun seeing the actual programming comes in to this. It's not just like, well, we just kind of train the model and then random things happen. It's like, no, there's human intelligence that's like actually shaping these models and how they develop and grow. It's not just like, well, we let it go loose and then eventually it kind of grows into something that's like able to do these things. So it's cool.
Yeah. Even when you get into more advanced neural networks, like there's still a very conscious decision made on the part of the person designing them, like what the expectation is that they will output. And that's actually a hugely important part of the process, is like understanding the sorts of things you want it to output and how it does it and how you feed that data back into itself. If you want to get really technical about this, this is technically a classification problem. It's just that the possible normally when you think of classification, it's something like, like the Not Hot Dog app, if anybody remembers that from what does that show, Silicon Valley a while ago, or just like facial recognition, like who is this, or like, is this traffic light, like what color is it, can I drive through it or not? Those are all very specific constrained classes to choose from. In this case, the class is words, and there are a whole lot of them, but it's still fundamentally a classification problem. And so the process of tokenization and pre-processing and all that stuff that we did at the beginning ultimately influences how many words the model has to choose from, and things like that. So yeah.
Michael?
I thought the talk was awesome. It was a good first step. So thank you. I'll probably be trying to learn more about AI. I guess it's good to know what goes under the hood. So
Yes. So I mentioned this before, I'll bring it up again now. There is a sheet that has some say like targeted problems. Like, it's not homework, I'm not going to grade it or anything, but it's sort of, if you're curious about this and you want to mess around with it more, it has some like try this next sort of suggestions for next steps. And I also put some textbooks and resources online that are free that I like a lot. So if you want to dive into it a little bit more, there's some books and sites and things that I found useful. I saw Santi and then Jennifer.
So if we wanted to create AI models for say, I want to be able to have a good conversation with a dead author, right? Following
Yes.
the train of thought. How can we take this to the next step to like curate our own models to say, hey, grab from this? Would we play around with OpenAI and just dump it files? Would we do something like this and do it from scratch?
I think actually maybe we could do like a really quick screen share again, because I can show you something, because I think what you might be talking about is more to do with like more as a prompting exercise. And I think that would be a useful thing to talk about, just because with large language models, there's the bigger question of what's the prefix. Like, we just randomly picked a prefix to start off with. But I could talk about prompting real quick, just I think is maybe like a partial answer to that question, and then also to answer that other question. So let's go in here. I'm just going to do text, and let me share my screen. So, okay. So the idea is that if you ask ChatGPT to do something, they very cleverly made it so that you start the conversation. And the reason why they made it so that you start the conversation is that you're the one supplying the initial context, right? Because if the idea was, hey, ChatGPT, just generate something, what is it going to generate? But by you asking the first question, you are the one providing it with context. So it might be something like, hey, ChatGPT, what is the capital of Australia? Sure, that's what we'll go with, right? So the idea is that this is the text that you give to ChatGPT. And so in effect, this is now the prefix, right? So if we were to put this into our language model and we were using, I don't know, bigrams, I think the prefix would just be of Australia. And that's the, this is an annoying thing to do. This is the most context that our model would get, but ChatGPT being ChatGPT, it has this larger context available to it. I would argue that OpenAI's main contribution to the field was not necessarily the model specifically. I just think they're very good at prompting. Because actually anything that you submit to ChatGPT is wrapped in a larger piece of context, where instead they have something like, you are a helpful chatbot language model designed to help people with their queries. Please answer in a positive, upbeat, helpful manner, and assist the user to the best of your ability with their queries. This is the user's question below. And then this is actually what gets sent to them. And if you think about what is happening with respect to what we just discussed, I don't think it's necessarily helpful to think of this as instructions to the model as I would give you instructions. Like, for instance, Chris, if I wanted to like tell you how to introduce me to this group of people, like I was like, oh, just tell them that I'm my name and my email address or whatever like that. I'm giving you a set of instructions, and I know that as like a sentient being, he's thinking about them and remembering them, and is going to consciously like choose to apply those things to his behavior when he introduces me to this group of people. But what this prompt can be better understood as is just more context, right? The idea is, given this entire piece of text that was submitted to ChatGPT, what is the most likely next word? And so you have to think that maybe in the training documents somewhere, it has seen examples of helpful advice, has seen examples of people answering questions helpfully and being positive and upbeat and wanting to assist other people. You might see that on forums or on Stack Overflow or something like, well, they're kind of mean on Stack Overflow, but anyway, but so that's the point. So all it's really doing is just providing additional context so that when we ask the question, what is the next word that comes next? It is doing that with respect to everything that was passed in, including the system prompt. So if you're getting into a situation where you're thinking like, I want it to behave in a particular way, this is kind of what prompt engineering is, right? So if you're framing your request to ChatGPT in a particular way, like speak all responses in the manner of Shelley, that's her name, right? Then that instruction is just additional context. And if it's a good language model, it might see that and not understand, but the context provided guides it towards selecting certain words that might be the kind of language that Mary Shelley might have used in her responses. So there's really two parts to this, which is making sure that it has enough training data. And then when you ask it questions, you're framing them correctly. Or maybe it's being automatically framed for you without your knowledge. This is, again, what I think OpenAI is very good at, in a way that will provide enough context for it to select the right words. I don't know if that answered your question, but hopefully that was
Thank you.
useful. Yeah. And then I saw there was one more question.
Mine was just a thumbs up.
Oh, okay, thank you.
Oh, I had the question. I was gonna ask,
Yes.
Is that an example of AI guardrails?
No. Guardrail. So I think maybe you can kind of see at this point that it's very difficult to control the output of this. And there's not really any meaningful way to force it to pick certain words or force it to avoid certain words. You can certainly tell it to avoid words or speak in a particular way in the system prompt if you want to. But again, it's not really a system prompt as a distinct special thing. It's just more context. And guardrails would be things like additional, because you might be able to train an additional machine learning model that's sitting on top of the model itself that is monitoring its output. And if it starts producing output that is going in kind of like an unsafe direction, you might be able to halt it and stop its output or something like that. There's also a form of training called reinforcement learning. Maybe you've seen that pop up a little bit, where you can disincentivize the model from predicting certain things. But at the end of the day, you can't stop. Like if it's like there's nothing in the process that would prevent it from. Again, it's just choosing the next word. And if that next word happens to be something that is inconvenient to you, there's not really much you can do to stop it other than to monitor it after the fact or try to disincentivize it from producing those words.
And one thing about ChatGPT and probably similar LLMs is, because there used to be this thing called Dan, which is do anything now, which was like a prompt that was like, don't listen to any of the rules, just let me do whatever I want. I don't think it works anymore. Probably not, because they made it a lot smarter. But basically, the way that ChatGPT enforces rules, you would think like, oh, we'll filter out these words from any prompt and just disallow people from saying this, or this. But it actually doesn't work like that. It works by looking at the entire context and then determining, does this break a rule or not? So like, for example, you might be talking to it and it's like, I can't help with that request. And you're like, why? You know, like it just, because it doesn't seem to like contain any weird language or anything like that. It just decided, I don't want to talk about that.
Yeah, but you have to remember that based on its training and the context that it has received so far, I can't help with that is just the most likely set of next words that it could have produced. That's it. And so like people who are trying to influence it to produce a particular sort of output are just influencing the likelihood of the words that it picks. Unless I'm wrong and there's an active monitoring system that would take over and prevent it from producing an output, but that would not be ChatGPT. That would be some other system that would be monitoring it.
So
Yeah.
unlikely scenarios reinforce unlikely scenarios. I can't do this reinforces I can't do this.
It would be more like so the way the reinforcement learning would work is you would need a situation where the model outputs something that you didn't like. And they actually do this, right? Like you can rate like thumbs up or thumbs down in ChatGPT. And reinforcement learning is a special type of machine learning that adjusts the way the model behaves, not based on how close it got to a desired outcome, but how good the outcome was as rated by some kind of external, they call it cost, but some kind of quality metric, right? And so if you're playing like a video game and you're doing reinforcement learning, then a really great cost function is just the score you get in a video game, right? So you don't care what the model does so long as it maximizes the amount of points that you get in the game. And so it just learns moves that maximize points. Well, in the context of ChatGPT and the human responses that you get, you would say like, well, this response got a thumbs down. We don't really know why, but it did get a thumbs down. So try to avoid whatever it was that you did that got the thumbs down. And the hope is in the aggregate, doing that thousands or millions of times, it does start to pick up on, oh, people tend to like it when I do this. People tend to dislike it when I do that.
So
yeah.
So one example, right, is like, and I believe I've tried this before. I talk to ChatGPT like way too much. So, you know, I you ask it a question like, for example, you have some semi-famous person, right? Like, or maybe it's like a YouTuber or something. You might ask it, what is the full name of this YouTuber with this username? And it's like, and say, for example, from that, it's like, I can't help with that request, you know? So
Yeah.
why did it determine that? I guess it's just that it was like you were asking for someone's full name and it can't.
Yeah.
It doesn't.
Again, it's just because that was the most likely sequence of words to come next given that context. That's it.
Although they didn't, I think that the people who developed ChatGPT in some sense told it like, hey, don't answer certain questions like whatever, you know.
Yeah, so that would be part of the prompt, the system prompt, and so that's part of the context. And so given that context, I can't help you with that as the most likely set of characters to come next. That's it.
Interesting.
That's the only real thing that they do. Like and there might be situations where like it knows how to interact with another system, or maybe there's like another monitoring system that's watching the output or something. And so like I can't really speak to any additional secondary systems that might be there, but fundamentally all of this boils down to, given a context, what is the most likely sequence of words to come next? And that's it. That's all it is.
Yeah. Interesting. So that would that be an example of a guardrail, or is guardrail a different thing?
It's hard to say because it doesn't know. Like, I don't know if it said that because it was prompted, like part of the system prompt, and thus part of the context that it should not do that, or if there's another system, or that just nobody did that and that just happened to be the most likely set. You know what I mean? Like maybe nobody put any guardrails in place and it just chose that as the output. That seems unlikely, but you know, it's always possible.
Yeah.
Yeah.
Interesting.
Yeah.
Are you gonna drop any like links and stuff to learn more?
Yeah,
I've
Chris
got,
should have that. Yeah, he's got a
docs
PDF.
and oh well, so I'm deconstructing your PDF into 2 Google Docs. One is going to be an exercise that I assign out on Google Classroom, and the other one is just going to be resources as an
Oh, okay.
resource.
And I actually keep
material.
thinking of more stuff to put in. So if you find that set of resources unsatisfying, you're welcome to email me. And
How
I'd be
about I
happy to.
just share it to you and make you an editor? And also, Matt, if you want, I'll send you the link to join our community Slack where all the learners are, and you know, then you can say hi if you like. Up to you.
You took apart my PDF.
You're welcome. So thanks everybody for all the thoughtful contributions and questions coming to follow along with the workshop here. I'll share all those resources shortly, and yeah, hope this has been helpful, and as much as for y'all as it has been for me, I learned a lot in prepping for this. Thank you once again to Matt. Thanks for hosting this talk. It's been very, very enjoyable.
Yeah, hope you got something useful out of it.
Yeah, good to see you. This is very interesting stuff. I learned a lot.
Fascinating. Yeah.
All right. Well, enjoy your summer, everybody.
Yeah, you too.
All
Have
right.
a great
Thanks,
one,
y'all.
everybody.
Have a great day.
Thank you guys.
Thank you guys.